Hello everybody. In this video, we're going to learn about directional derivatives. So in earlier lessons, we've been given a function z, a function of x and y, and we've learned about the partial derivatives dz dx and dz dy. Those both measure the change in z, we can think of as the change in height on a surface, as either x varies or y varies. Or if you want, you can think of dz dx as the change in the direction 1, 0, while dz dy is change along the direction 0, 1. The goal of this lesson is to learn how to measure the change in z along any direction, not just the coordinate axes. So we'll measure the change along the direction vector u, which is going to represent a unit vector. So we choose u to remind us that we like to do unit vectors. So in general, we're trying to answer the question, if you're hiking on a mountain and maybe you go north by northeast, right, how quickly is your elevation changing? So you might recall that the definition of the derivative in multivariable mathematics, well, it's still the limit of a difference quotient in both cases. The partial derivative df dx is the limit as h goes to 0, and h is added to the x component within your function. So in other words, the change h is applied to just x. Meanwhile, to calculate df dy, and we're taking a look at a limit as h goes to 0, but here the h is being added to the y. Now, the way we'll define a directional derivative, rather than appending all the change to x or adding all the change to y, we'll define this. We'll use the symbol d sub u of f, capital D for derivative, and the vector u indicating what direction we're calculating the derivative in. This will also be a limit as h goes to 0, but this time it's going to be f of x plus h times u1, comma, y plus h times u2. And so in this case, it's like a little bit of change is being added to the x and to the y, right? Some factors being multiplied by h in both cases. And here, I'm using the notation x naught, y naught. That just means they refer to particular values, right? So we're calculating the derivative at a specific point using this formula. So graphically speaking, here's my three-dimensional x, y, z axes. Here's my favorite three-dimensional surface, z equals f of x, y. And here we have a point, x naught, y naught, down here, and some direction, the vector u. Now this point x naught, y naught, when we plug it into the function f, that gives us a z value. So we have a point on this surface. If the x and y change in this direction, well, in this case we'll probably be moving up the hill a little bit. But the question is, how much? And that's what the directional derivative will tell us. And so our goal is to calculate this expression. And to do this, we're going to break it up into parts. Right? First, since we're talking about moving in a particular direction of a line, let's actually write down the equation of a line. Let L be the line in the direction u that passes through the point we're interested in. It passes through x naught, y naught at time t equals 0. Well, writing down the equation of this line is pretty basic. We've been doing this for a while now. L of t is equal to the direction vector u times t plus this point. And when t equals 0, right, the direction times t cancels out, leaving us with just this point. So L of 0 goes through this point at time t equals 0, just as we wished. If you wish, you could also take this expression and collapse it into one vector by doing the scalar multiplication, multiply each of these by t, and then adding together the components. This could be rewritten as u1 times t plus x naught, comma, u2 times t plus y naught. Now, if we do the composition of these functions, We talked about this a little bit when we discussed the chain rule, right? The composition of a multivariable function and a vector function gives us a curve on the surface, right? And so that curve, we'll call it g of t. And g of t, well, it passes through the point that we're interested in, x naught, y naught, and it's traveling in the direction u that we want to calculate the derivative in. So the derivative of this function g of t gives us exactly this directional derivative that we're interested in, right? It's the rate of change of this function in this direction. And so it's kind of a geometric explanation. If you prefer a more algebraic explanation, if you wanted to calculate the derivative of g at time 0, again, you'd use this limit as h goes to 0. And that's a difference quotient, g of 0 plus h minus g of 0 all over h. And 0 plus h, well, that's just h. We can replace g, the function g, with a function f of l. Right, so here we have f of l of h replacing g, f of l of 0 replacing g, still divided by h. And then what is f of l of h? Well, that's exactly what we're trying to calculate. And what's f of L of 0? Well, L of 0 is x naught, y naught, which is exactly what we're trying to calculate. So this works out very well. Now, in order to calculate dg dt, which gives us the directional derivative, g is a composition of functions, which means we need to use the chain rule. Since the function, right, f depends on x and y, and x of y depend on t, we have this dependency diagram. Right? F is a multivariable function, f depends on x and y both depend on t. So the chain rule for this diagram would say that dg dt, or df dt if you wish, would be df dx times dx dt, and that's the change along this chain, plus df dy times dy dt. That's the change along this chain. All right, so L of t, remember that gives us the x and y coordinates, so it's these two functions right here. X is this first component function, x is u1 times t plus x naught. u1, x naught are both constants, t is your variable, so the derivative of x with respect to t is just this constant, u1. Similarly, the derivative of y with respect to t is just the coefficient of t, the constant u2. So the chain rule says that this derivative, right, we know what dx dt is, we know what dy dt is, that's u1 and u2. So that's the formula for the directional derivative. If you think about it, it kind of makes sense intuitively, in that if you're not traveling in just the x direction and not just the y direction, but some combination of those directions, the rate of change, the combination, is going to be some combination of the different rates of change. And the coefficients will make sense. How much are you traveling in the x direction? Right, that's your multiplier for df dx. How much you're traveling in the y direction? That's your multiplier for df dy. And that's how you calculate a directional derivative. Now let's put this theoretical knowledge to use and let's do an actual exercise. So what's the directional derivative of f of xy, the multivariable function, x squared times y cubed at the point xy equals 3, 2 in the direction 3, 4? Now before we begin, just as a standard, we're always using unit vectors for directions. And this vector, 3, 4, is not a unit vector. Right, so what we always want to do is, if our given direction is v, we want to convert v to a unit vector u. The way we do that is we divide the components of v by the length of v. So for example, the length of the vector 3, 4 is 5. And therefore, the unit vector will be the vector 3, 4 divided by 5, which is the vector 3/5, 4/5. Now, the partial derivatives of this function we may have seen it once before, df dx is equal to 2xy cubed, evaluated at 3, 2, and that derivative is 48. df dy, that partial derivative, is 3x squared y squared, evaluated at the point 3, 2, we get 108. And now we can put these pieces together, right, the values of the partial derivatives together with the components of our unit vector. The derivative of f at 3, 2 in the direction u is equal to, 48 times 3/5 plus 108 times 4/5. If you add that up, I think it's 576 over 5, which is 115.2. And so this is the rate of change in that direction. Interestingly, it's actually higher than the rate of change in either x or y. Now that we have the directional derivative in any direction, we can also calculate the equation of a tangent line in any direction. Right? Before, we just knew partial derivatives, and that meant we could only calculate tangent lines in those two directions, the x-axis and the y-axis. But now we can get all the tangent lines. So, as always, remember the equation of a line, a parametric equation, is L of t is equal to the slope vector m times t plus a point p on that line. So to calculate p, well, if you get your given values of x and y, to get the value of z, you plug your given values into the function f. The slope vector in this case, well, again, you're given u, and this tells you your change in x and your change in y, but then you have to calculate the directional derivative to get the change in z. And just as a fun side note, if you went through this calculation, say for the vector u is a vector 1, 0, what would the directional derivative be? Well, according to the formula, du of f would be df dx times 1 plus df dy times 0, which is just df dx. And that answer algebraically agrees with our intuition. Right? The derivative of f traveling in the direction 1, 0, that's traveling along the x-axis. So that derivative should just be the partial derivative with respect to x. Similarly, if you were interested in calculating the directional derivative in the direction 0, 1, you'll find that the directional derivative du of f is equal to df dy, the partial derivative in the y direction, which again makes sense because this vector 0, 1 points along the y-axis. All right, as one more example of calculating a tangent line, let's calculate the tangent line to f of xy is equal to x squared y cubed at 3, 2 in the direction 3, 4. Of course, I'm picking this example because it builds on our previous work. Right? We know that the unit vector is 3/5, 4/5, and we already calculated the directional derivative to be 576 over 5. Well, that means we know our slope vector, right? It's the components of u, and so 3/5, 4/5, and the directional derivative, 576/5, so it's a pretty steep hill. And then the point, well, we have our given x value 3, our given y value 2. Plug these into f, we'll find that the corresponding z value is 72. Then we just assemble the pieces into the equation of a parametric line. And that's the equation of the tangent line in the direction 3, 4. Now, you might be given the direction in terms of other values. Kind of like when we first started talking about unit vectors, you can calculate a unit vector if you're just given an angle measure. So for example, let's say we want to calculate the tangent line to this multivariable function, x squared plus 3xy plus 4y squared, at the point xy equals negative 1, 1, in a direction that makes 30-degree angle with the x-axis. And so here's the diagram on the left. Here's our x-axis. We want a vector pointing at a 30-degree angle from the x-axis. Well, the equation of this is going to be cosine 30 degrees sine 30 degrees. Actually, those numbers are 1/2 and radical 3/2. So, right, that's going to be our unit vector u. We also need partial derivatives. Right, the partial derivative of this function with respect to x. X is your variable, y is a constant. The derivative of x squared is 2x. The derivative of a constant times x times a constant, that's just the constant part, 3y. The derivative of a constant is 0. As that completes the partial derivative, df dx. You plug in the values, -1 and 1 for x and y, you'll find that df dx equals 1. To calculate the partial derivative, df dy, and y is the variable, and now x is the constant, the derivative of x squared is 0. The derivative of a constant times y is that constant. The derivative of 4y squared is 8y. And so there's our partial derivative. Again, plug in the values -1 and 1 for x and y. We'll find that df dy equals 5. And now with all these values, we're ready to calculate the directional derivative. So du of f is df dx times u1 plus df dy times u2. So in this case, right, df dx is 1, u1 is 1/2, df dy is 5, u2 is radical 3/2. Combine these values, you can put them in a single fraction. The quantity 1 plus 5 radical 3 all over 2. So now we have our slope vector, 1/2 radical 3/2, 1 plus 5 radical 3/2. Our point, we'll take our x values, -1, the y value 1, plug them into f to get the z value, which turns out to be 2, and there you have it, the equation of the tangent line and that angle. Now, one interesting thing you might have noticed, always pay attention when something looks like a dot product. Right? The directional derivative here has the form of a dot product. And as we've seen many times before, interesting things are afoot when dot products appear. And so in this case, we could actually write the directional derivative as a dot product. The vector containing partial derivatives dot with a vector u1, u2. And this actually has a name. This is our unit vector u. But the vector of partial derivatives is also important for many reasons. And it's given its own name. This is also called the gradient of f, kind of like the gradient of a hill. Right? It somehow contains steepness information. It also has a special symbol. It's written as this upside down triangle of f. Right, so we can write this expression. Du of f is equal to the gradient of f dot product the vector u. So, given a function, we can actually just calculate the gradient if we wish, which we will wish to do for a very specific reason sometimes. So let's see. We need the vector of partial derivatives of this function. Right, the partial derivative of f with respect to x, that's going to be 2x plus the derivative of this part is 3y. Then the partial derivative with respect to y. This first part, the derivative is 0. The second part, the derivative is 6xy. So in the previous example, see at the point xy is equal to 1, 1, we want to find the unit vector u so that the directional derivative is largest. Right, so let's say we're given this specific point. It's as if you're standing on a mountain. At this location, you want to choose the direction, choose the vector u, which corresponds to the largest derivative. That means the maximum increase of a function at that point. If you want to get to the top of the mountain most quickly, what direction must you go in? So, when xy equals 1, 1, the gradient is equal to the vector 5, 6. Now, let's think and let's recall to mind some things which we did a long time ago. Right? The directional derivative of f is the gradient dot with u. So it's the vector 5, 6 dot u. Now, draw a graph of these two vectors, right? The vector 5, 6 and the vector u. There's an angle theta between these two vectors. And a long time ago, when we first started learning about dot products, we learned a formula to calculate the cosine of the angle between the two vectors. The cosine of the angle was the dot product of the vectors divided by the length of these vectors multiplied together. And we actually know the length of a unit vector. The length of a unit vector, no matter what we choose for u, that's going to have length 1. And dividing by 1 or multiplying by 1 does not change a value, so we can actually just drop this from the equation. So, if we were to rearrange this a little bit, we would see that 5, 6 dot u, and we could move the length of 5, 6 to the other side of the equation here. 5, 6 dot u is equal to the length of 5, 6 times cosine theta. So we could replace this dot product with the length of 5, 6 times cosine theta. Now remember, we want to make this as large as possible. Finding the direction of maximum increase is our goal. Well, we don't really have any control over the magnitude of 5, 6, right? That's going to be some number. The cosine of theta, though, we can make that as large as possible. The largest possible value of cosine theta is 1. Right, so this expression is maximized when cosine of theta is 1. That happens when theta is 0 degrees. Well, what does that mean in this picture over here? If theta is 0 degrees, that means, well, the angle between these two vectors is 0. These vectors are aligned with each other. So the vector u should point in the same direction as the vector 5, 6. The vector u, well, since it should be a unit vector, must be this vector. 5 over radical 61, 6 over radical 61, because the length of this vector is the square root of 61. So that tells you the direction of maximum increase for this function. And this generalizes easily as well. In general, the directional derivative of a function can be written as the gradient dot product a unit vector. And we still have this same diagram. The gradient is a vector, and that's going to have a fixed value. Right, we're going to be evaluating the gradient at a specific point. It's the direction, the unit vector u, that we're allowed to choose. There is some angle between these two vectors, call that angle theta, and to calculate the cosine of that angle, that's equal to the dot product of the gradient and the unit vector divided by the length of the gradient times the length of the unit vector. That's always 1, so we can drop it out. Rearranging this equation, we have the length of the gradient, which is some constant, times cosine theta, which depends on u, is equal to the gradient of f dot u. So we can replace the gradient of f dot u with this expression. The directional derivative of f is equal to the length of the gradient times cosine theta. Since the length of the gradient is a fixed constant, this expression is maximized when cosine theta equals 1, which again means that theta is 0 degrees, which again means that the unit vector u, to maximize it, should be aligned with the gradient. Right? The takeaway sentence here is that the gradient vector points in the direction of fastest increase. All right, that's an interesting side note, but I think the most important things to take away from this lesson are: how do you calculate a directional derivative, and how do you come up with the equation of a tangent line? And so the review exercise for this lesson is to do exactly that. Let's say you're given this function, f of xy is equal to x squared times y minus y cubed. Calculate the directional derivative of this function at the point 2, 1 in the direction 1, 1. And remember, you need to convert this direction to a unit vector. Once you have that value, find the equation of the tangent line to this surface at this point in this direction. And that'll use the directional derivative that you previously calculated. And then, once you're able to finish this, you now know how to calculate a tangent line to a surface in any direction with the help of the directional derivative. That's it for this video. Thanks for watching.